Okay, for problem number 17, we're given a graph, which I've done my best to recreate here on the board. And we need to identify a lot of things about the function. So keep in mind we are looking at the function f of x, and we need to figure out a bunch of different things. So first, part A says we want to identify where the function is increasing. So what that means is as we move from left to right along the graph, if our y value is going up as we move, then we are increasing. So let's think about all the intervals where we're increasing. So starting at the furthest left you can go in the graph, we're always going to be increasing up to this point here, which is at x equals -4. So our first interval of increase is -infinity to -4. So all the way left as far as you can go up to -4, we're increasing. Starting at x equals -4, we become decreasing. So we're increasing again starting at x equals -2, because as we move to the right from the bottom of this parabolic shape there, as we go to the right, it's going up again. But we have a hole at -1 where we stop, so we actually have to stop increasing there. So we're increasing from -2 to -1 as well. As we resume on the other side of the hole, we're now increasing still. At x equals 1, the graph goes flat, so it actually stops increasing at x equals 1. So again, we're increasing from -1 to 1. When we get to x equals 1, after that we're increasing again, all the way up to x equals 3, where it hits this point. So 1 to 3. And then after that, the function is always decreasing. So these 4 intervals are where our function is increasing. So B, let's figure out where our function is decreasing. So it's decreasing. This is all increasing. The first time it starts decreasing is x equals -4, and it decreases up to x equals -2. So our first interval of decrease is -4 to -2. Everything else here was increasing or just a non-included point along the way. And the last time we are decreasing is from 3 to infinity. We're decreasing everything past that. So we have 4 intervals of increase here, and we have 2 intervals of decrease. So part C, we want to know, where does this function have horizontal tangent lines? So horizontal tangent lines would occur every time the tangent line to the graph would be horizontal, and that means that our derivative would be 0. But let's think about what that means graphically speaking. Remember that the tangent line is something that essentially is the slope of the graph at any given point. And in any case, if you were to kind of zoom in on the graph and make it into a line, that line would be the tangent line. So it's going to be 0. We're going to have horizontal tangent lines at the bottom of this parabola part here. We're also going to have a horizontal tangent line where the graph flattens out right here. That would be, if we drew the tangent line to the graph, it would be horizontal there. And that's it. We're not going to have horizontal tangent lines anywhere else. So our horizontal tangent lines are at x equals -2 and x equals 1. So those are the x values where we have horizontal tangent lines. So part D, where do we have vertical tangent lines? So again, now as we just go along the graph and try to imagine what our tangent line is doing, we want to see where would we have a tangent line that's vertical. Well, we would have a vertical tangent line at this cusp right here. Because you can think of as this graph curves up, eventually it becomes just about vertical at the point and then comes back down the other side. So our tangent line right at that point would be vertical. We would also have a vertical tangent line right over here where our graph actually goes vertical for 1 point and then continues curving. So we have 2 vertical tangent lines, one here and one here. So those are at x equals -4 and at x equals 5. 2 horizontal tangent lines, 2 vertical tangent lines. All right, for letter E, we have Where is the function not differentiable? All right, so this is the most interesting one of what we've come up with here so far. Where is the function not differentiable? So this is where is the derivative undefined, or does it not exist? So this is going to be a few places. So first of all, anywhere that we have a vertical tangent line, we immediately have a point where it's not differentiable, because the slope of the tangent line, if it's vertical, think about what the slope of a vertical line is. The slope of a vertical line is undefined. So that means that the derivative, because the derivative is the slope of the tangent line, at those 2 points would be undefined. So that's not differentiable. So we definitely have the 2 vertical tangent line points. Let's think about other places where this would be not differentiable. It's definitely not differentiable at this hole here, because our function doesn't exist there either. So if we tried to take the slope of the tangent line at a point that is not even on the graph, we can't do the derivative of that. So that's a point where the function is not differentiable. We have one other point where the function is not differentiable, and that's this corner point right here at x equals 3. So the difference between this point and the one at x equals negative 4 is the one at x equals negative 4 is called a cusp, because the lines become vertical as they touch. This point at x equals 3 is called a corner point, because the tangent lines as they're approaching the point are just very well-defined lines, one's like this and one's like this. They have definite finite slopes, but they meet at the 2 slopes just connect at one point instead of smoothly going like at any other point in this graph. So that's called a corner point, and that is also not differentiable. So here's why that's not differentiable. For a point to be differentiable, the limit of the derivative from the left and the right have to be equal. Think of it as the same kind of thing as continuity. So a function is continuous if the y values are approaching the same point from left and from right. So a function is differentiable if the slopes are the same value from left and right. So this corner point right here is definitely continuous because the function meets the y values at the same point. However, the slopes do not approach the same thing. From the left side, our slope is some positive value here. From the right side, our slope is from some negative value, and they just meet abruptly. Not the same slope from each side, so that's not differentiable either. So we have 4 total points that are not differentiable here. We have x equals negative 4, because that's the first vertical tangent line. We have x equals negative 1, because that's where we have a hole. We have x equals 3, because that's the location of our corner point there. And we have x equals 5, because that's the location of our other vertical tangent line. So we have 4 different points where this function is not differentiable. So the last part of this question is to use these answers to sketch a possible graph of the derivative. So I'm going to try to do that on the same graph here so you can see how it relates to the graph of the function itself. Try to erase all my dotted lines as much as I can. Okay, so let's figure out what our derivative looks like. So let's label some important points on here at first. And I'm going to do this in a different color, and hopefully it's dark enough to be seen. Okay. So any place that our function has a horizontal tangent line, remember that means that our derivative, the slope of the tangent line, would be 0. So if we're graphing our derivative, at x equals negative 2, we had a horizontal tangent line. So that means our derivative value is 0 there, because the derivative is the slope of the tangent line. Also at x equals 1, because at this point is where our graph flattened out, it has a horizontal tangent line, so the derivative has to be 0 there. So the derivative crosses our axis. It's 0 at this point and at this point. Anytime we had a vertical tangent line, that means our derivative is undefined. That means our derivative is going to have a vertical asymptote. So at x equals negative 4, our derivative has a vertical asymptote. And at x equals 5, our derivative has a vertical asymptote. Because as we approach from either side, our slope is going to infinity or negative infinity depending on the side. So that's going to be a vertical asymptote in the derivative. And the other 2 points, we'll work that out as we go. So what we can think of here is, look on the left side, this function is increasing. As far left as you go, it's always increasing. That means that the slope is positive. That means our derivative is positive. So our derivative is always above the y-axis because it's always positive. But as we go along, it gets steeper and steeper, which means it gets more and more positive. So what this is going to have to look like is something like that. So this is positive, and as we get closer to this, it gets more and more positive up to infinity at the actual cusp. Let's think about what this looks like now coming off the cusp. As we come off the cusp, our slope was vertical, and now it's extremely negative and gets less negative as we go on. So this is just going to look like the other side of the vertical asymptote. And it's going to connect right here because we know at this point our derivative had to be 0. So it has to be 0 right there. After this, it's going to be positive. But we have to come back and hit 0 here. So it's going to have to go up and down. However, at some point where we had this hole, we also have a hole in the derivative because the derivative just doesn't exist at that one point, but it exists everywhere else, and otherwise it would be smooth. So any hole in your function also looks like a hole in your derivative. So we were positive here because this function's increasing. It's increasing, so our derivative is positive. And now our derivative is 0 because we got back to being a slope of 0. So remember, this green line is essentially just trying to place a value on the slope at every point. So after, let me try to make this a little bit more smooth. After this 0 point, we're back to increasing again. So this is actually going to hit this and come back up. Because now our derivative has to be positive here. And at this point, right here, where we get the corner point, this is where this might be a little bit tricky for the derivative. Think of it like this. Our derivative is positive, and all of a sudden, as we cross this corner, it just immediately becomes something negative. So what this is going to be is it's going to be a jump in the derivative where we just go from positive to negative instantly with no smooth transition. What happens after the jump? It's negative, so that's why I put the hole down here. But now let's think about which way is it going from here. Well, on the right side of the corner, the slope is negative, and it's getting more negative. It's getting steeper, so this has to be going down like that. Remember, we already drew the vertical asymptote for the derivative there because we know that at exactly x equals 5, our slope is infinite, so there has to be a vertical asymptote. On the left side, it's decreasing, becoming very, very negative to be infinite, so it's down. On the right side, though, it's still decreasing after that. So now our derivative, our slope, still has to be negative, so it has to come off the vertical asymptote from under. And as you can see, what this graph looks like it's doing is it's flattening out, so its slope is getting less negative. In other words, closer to 0. So this green line that I've drawn here, this is an approximation of what your derivative might look like. So the important parts are not exactly what y value I hit at any given point, but that I got the jump correct, I got the asymptotes correct, I got the hole correct, and I got our x-intercepts correct. If you have all that key information correct, the rest of the line doesn't need to be perfect for you to get full credit on this on a test. So as long as you realize that when you're drawing the graph of the derivative, just imagine that you're drawing the value of the slope at every given point. The key information should really be clear to you, and I hope that it is based off of what I talked about on this graph.
The Teaching Center, UF's Learning Resource Center.